Welcome to In 5 Minutes. We take problem on temperature stresses. Our problem statement is a steel bar is placed between two copper bars, each having the same area and length as the steel bar at 15 degrees centigrade. At this stage, they are rigidly connected to each other at both ends. When the temperature is raised to 315 degrees centigrade, the length of the bar increases by 1.5 mm. Determine the original length and final stress in the bar. The properties of the material, steel and copper bar, is given as ES is 2.1 into 10 to the power 5 Newton per mm square, EC is 1 into 10 to the power 5 Newton per mm square, alpha S is 12 into 10 to the power minus 6 per degree centigrade, and alpha C is 17.5 into 10 to the power minus 6 per degree centigrade. So we first draw the figure for the problem. So you can see here in this first figure we have this steel rod and two copper rods, and these two rods are rigidly connected to each other by means of this bar. Now when this copper and steel bar is being heated such that its temperature rises to 315 degrees centigrade, so your resulting delta T becomes 315 minus 15 degrees centigrade equal to 300 degrees centigrade. Now due to this heating, both the steel and copper bar will try to elongate or expand. Now since linear coefficient of thermal expansion for copper, alpha C, is greater than the linear coefficient of thermal expansion for steel, alpha S, you will find that the free expansion of copper bar will be greater than that of steel bar, as shown in figure 2. Now since in the problem it has been mentioned that the two bars are rigidly connected to each other, you will find that the deformation or elongation of the composite bar must be equal. And also it has been given in the problem that the deformation or elongation of the composite bar is 1.5 mm. So you can see in this figure the delta L or elongation of the composite section as 1.5 mm. Now a little consideration will show that the final position of this rigid bar will be somewhere in between the free expansion of steel and free expansion of copper. Meaning that the copper bars, the two copper bars, has been slightly contracted, whereas the steel bar has been slightly elongated. There is a compressive load developed on the copper bar, whereas the equal and opposite tensile load developed on the steel bar. And the compressive load on the copper bar must be equal and opposite to the tensile load on the steel bar. Its magnitude will be equal. So now let's solve the problem. First write all the given data. Area of copper rod is same as that of area of steel rod, and delta L they have mentioned as 1.5 mm. And the properties of this copper and steel bar is visible over here, so we won't be writing here. And in this problem we have to find first the original length of the bar system L, second the stresses induced in both the bars, steel and copper bar, that is sigma S and sigma C. So let's start with the solution. Now as alpha C is greater than alpha S, we have tensile load on steel is same as compressive load on copper. So we first start with the static equilibrium equation, which is nothing but the force balance equation, as a steel and copper bar together constitutes a statically indeterminate structure. Now we'll first assume that the load on the steel as well as copper bar is tensile. So we write the equation in this way: PS, which is the total load on the steel bar, plus PC, which is the total load on two copper bars, is equal to 0. Why? Because there is no external load applied. So we can write it as PS is equal to minus of PC. Now this is the same thing as we have written here. Suppose we have load on the steel as tensile load, PS as positive, so the resultant load on copper bar will be, if this minus sign comes here, it will be negative. So we have PS as sigma S into AS is equal to minus of 2 sigma C into AC. This 2 comes here because we have two copper rods. Therefore we have sigma S is equal to 2 sigma C. Now AS and AC gets cancelled since it is given that AS is equal to AC. Now let this be equation 1.